Alright, today we're going to speak a little bit about our completed mechanism, including gearbox attached. The gearbox, again, is a very large ratio of 26,100 to 1. When we did the calculations on this gear ratio, the back 3 or 4 sets of gears failed due to surface stresses and bending failure. But with time constraints, we were unable to alter our gears, so we went with this gearbox just to show how it would attach to the mechanism itself in complete assembly. We've got an animation that we're going to show you. This animation is approximately 220 seconds in reality, but it's 400 frames. So it takes a long time to complete because it's ultimately the 220 seconds for 20 frames a second. So we're going to go ahead and start the video, and we'll just discuss the mechanism a little bit again while it's going. First thing I'll show you guys is, after we've started the mechanism, is one, of course, the frame rate is still so low at 20 frames per second that you can't see the input spinning. You can see the involute curves rotating about the shaft. For the second gear, you can still as well see the involute curves rotating about the shaft, but not quite catch the gear moving, unfortunately. And for the third, fourth, fifth, sixth, and seventh gears, they're moving fairly readily because of our reduced frame rate, just so you're able to see the mechanism actually operating. If we move further down the mechanism, we actually attach to the base and the driver dyad right here. In reality, we'd use a little shaft collar. We'd probably cut flats on both sides to attach this, but for our purposes here, this works just fine. This attaches to the driver dyad, which has rotated itself about, but currently would be 180 from this, so that it has no interferences. Attached to that, again, is the slider slot mechanism. There is an arm that ultimately pushes a pin. So to talk a little bit more about this particular slider arm, we use a large radius curve, and this curve is the driving line for the slot itself. The curve allows us to have a continuous path of motion and input of force in one direction, instead of having it potentially fall back the other way due to increased forces from lifting the weight itself. This system works by having multiple slots. I'm going to try and angle this so we can see the slot underneath. So the slot underneath attaches to the pin. It's green. The green pin attaches to a linear rail on the inside that ultimately would run on ball bearings, so this system would be very smooth. We'd try and ultimately reduce friction out of this as much as possible, and that would allow for us to ultimately get the weight over the wall with reduced torque output, hopefully. Again, we're only about 600 frames in now, but we're just cruising along up our linear trail here. Our arm, when we did stress analysis on it, had a little bit of a failure issue right at this location where it rides along the barrel cam. So we've decided that here in a little bit we're hopefully going to be redesigning this with a larger surface area, because we chose to use about 2.5 millimeter tubing across the whole thing, which is very thin. If we beef that up a little bit, hopefully we won't have any failures with lighter weight metals. Our weight, again, is still being attached to the end effector via a forklift method, where it scoops the weight and will rotate up through this angle from the beginning of its path to the very end of its path over the wall, to then dump the weight as the end effector is caught on the wall a little bit on the backside. You can see this very well if we go on some of the other sides of the mechanism, particularly this view. You can see the angle of the weight is slowly increasing to where we will ultimately get it just over the wall. So we had a little bit of trouble modeling this system, because you have to ultimately go from having a straight armed end effector to having one that is upwards angled enough so that it clears the wall. So to do this, we had to do a little bit of planar geometry and play with some tricks. The arm itself, in reality, would ride along the barrel cam fairly easily, in my opinion, and it's not so much an issue. In Creo, however, you're required to make a barrel cam by using surface modeling techniques and projection. So we project a line onto a surface model to create a path for the cam itself, and then we have a point on the component item follow the path of the cam. So this is great, however, it constrains it much more than it would in reality. And that's why in some of our graphs, when we start showing and outputting some of those here in a minute, some of our graphs have increased values at the end where it dumps the weight, because it's being driven down due to this cam system versus in reality where it would just fall down via gravity. I'm going to go ahead and speed up our frames just a little bit and accelerate us in time some, so that our weight is a little bit closer to clearing the wall. But ultimately our mechanism is made in this manner so that we can have a return. The slot that is cut further into the barrel, and on the other side allows for the end effector, once it dumps the weight, to be knocked over to the other side and just ride its way back and be knocked over back to the original side in a really smooth manner to keep picking up weights in an assembly line fashion. One thing that we've considered certainly is, in reality, when we were speaking to the machine shop guys and people from the past, our peers, they suggested that we extend our time and we shoot to get the weight over one time in reality, because most people are unable to do it at all, which is why we chose to do a high gear ratio. It's why we chose to try and reduce frictional effects anywhere and everywhere that we could possible, and that's why we tried to use a cam system as well. We believe that this is just going to be the most effective means of moving the weight in an industrial setting that we could make. But here in a few more seconds, the weight will go ahead and start dropping. But to speak more on designing this mechanism, we had a lot of trial and error with designing particular components, especially the slider arm. Getting that angle of curvature correct took quite a long time with trial and error until we found the correct angle that was necessary. We tried different locations for pin placement for the beginning of that arm as well. So this mechanism really was kind of a tried and true creation from us, instead of trying to copy some individuals from online. We took inspiration from what we found online and inspiration from what we were told, but tried to do it a little bit one-off. And I hope you guys like it, and I hope forward seeing y'all in the future. That's it right here. So this is where the mechanism would be dropping the weight, and our end effector would be interfering with the wall, as well as the weight interfering with the wall to knock the weight free of the end effector to ultimately make the return path that we spoke of earlier.